Okay, so I see 4 people. Okay, we are connecting. Great. So just two more. No, I think, okay, three. I think we are going to be three, right? So we are all here. Excellent. Okay, so welcome to this session. Will be the first class on complex networks. As Alejandro, I guess, told you, we are going to have 3 sessions. So this week, next week, and the week after. So I'm Massimiliano Zanin. I used to be a postdoc researcher in Alejandro's group here there at UPM, sorry. Then since March, more or less, I moved to IFISC here in Palma de Mallorca. So I'm here right now, as you can see, with a good sun behind me, and the beach and the sea is not very far away, but I will stay here a couple of hours with you. And just to make a short introduction, would you please tell me just a couple of words about what is your background in what you use, what you have studied, or what is your general background, just to have an idea of what or if there are topics that may be more difficult for you or less difficult, or so who starts? Mm-hmm. Okay. Okay, that's good. Perfect, perfect. Well, take into account that nowadays it's difficult to find something that is not related to data. I mean, even agriculture or whatever is everything is related to data. So, but good, okay. If it's medical data, even better. Okay, next one. Mm-hmm. Uh-huh. Nice. Mm-hmm. Okay, perfect. Third one. Mm-hmm. Okay, perfect. Just a general question. I understand that you three have a good knowledge or a decent knowledge of programming, like Python, for instance, things like that. Okay, but I think basic will be okay. Yeah, we don't need the super complicated programs. But the idea is more or less that in this first day, so today we will just see an introduction of complex networks, what they are, why we want to study networks. We will use a program that I sent you, Cytoscape, to just plot networks, and is usually a first good step, a good first step at least to analyze network. Then in the next week and the week after, we will try to analyze, let's say, more numerically networks. So we will reconstruct network and we will try to extract some feature from them. And for that, you will need a little bit of Python, but it won't be super complicated, just some basic Python. Okay, so I would say that without further ado, unless you have some questions, we can move to the presentation that I had for today. Uh, that is this one. I cannot, while I have the presentation on, I cannot see your face. So, but in any case, if you have any question or whatever, just stop me and we can discuss. So, first of all, then network analysis or networks. What are networks? What are these complex networks that this? Yeah, yeah, please. Uh, sorry, I'm not sharing it. You are perfectly right. Uh, Wait, how is the sharing here in this program? Open share tray. Okay, perfect. Okay, sorry. I need just 1 second to give permission to this program. Uh, I'm using a Mac, and as you know, Mac is quite, uh, and I don't see how. Interesting. Okay, so, okay, so I have to do this, upload from my computer. Okay, for some reason I cannot share it. Good. Okay, 1 second. I think I have to restart Teams. So give me just 1 second, I will be back. Okay, I should be back. And now let's see if we are more lucky and I can. Okay, I can just. So you can see my screen now, which is something, and you can see now the presentation. Okay. Thanks God. You never know what what problem will appear. Okay, so let's go back to business. So network analysis. Let's start with what are networks or what are complex networks more specifically. Well, the idea of networks is quite old. Is a quite old one. Actually, it started in from graph theory that was introduced in 1735, more or less, by Euler, a very famous mathematician. And the point is that at that time, people were trying to solve what is called the seven bridges of Königsberg problem. So the idea is the following: there was this city, Königsberg, that was in, well, it's still actually in Russia. It has another name right now, but the city is still there. And as you can see from this very simplified picture, the point is that it has like four lands, let's say parts of the city that were connected by bridges because it had one river that was like crossing the city and splitting the city in several parts. So you have these four lines that where you can be, and then you have should be seven bridges. Now, and the problem was, can I move from, can I start from one place of the city, visit all the four lands, and get back to the original one without passing twice in any one of these bridges? So it was like a game that people tried to solve, and the solution was that actually you cannot do that. But the important point is that Euler demonstrated this solution with a very simple idea. Instead of analyzing this as a problem, a complex problem in which you have to move inside a city and therefore you have a lot of different things that you can consider, let's just abstract and let's just consider that each land or each bridge is just one entity. And I don't care which land is it or which island, if it's the island in the middle or another one, which bridge is it. I don't really care about all of this. So he created a very abstract representation that is the one on the right, that is what is called now a graph, in which you have that land masses, let's say, are nodes, and are connected between them by edges or links when you can move from one node to another one. But the important point is that you don't know or you don't fix a priori what these nodes or these links are. They are just entities, they're just a set of entities that are connected between them. Now, this is quite interesting because then uh, a few years later, actually many years later, we are talking about the year 2000 or 2006, more or less, this idea of graphs was imported or let's say used by people working in statistical physics, and they evolved the idea of graph into what is now known as complex network theory, in which a complex network is a mathematical object in which we have nodes that are the elements of the system that we are studying, and these nodes are connected by links, which represent the relationship between pairs of nodes. The good part of this is that we don't care what nodes are and what links are. We just know that we have a system in which there are some elements that are related between them, and we try to analyze the structure created by these relationships. But we don't care if nodes are, for instance, social interaction. So in this case, nodes can be people connected by between them if they are friends together in a social network, or if we are talking about neurons in the brain that are connected together by synapses, or we are talking about, like in the power grids, we have different power generators connecting together by power lines. We don't really care what these elements are. We just know that there are some elements that are connected, and we want to study the structure created by this connection. So this is strongly related with a completely different theory, that is the Gestalt theory. Uh, Probably you know this is a social science, especially a psychological theory that says that perception are the product of complex interaction between various stimuli, and that when you see something, you don't just see a collection of unrelated elements, but what you see is actually the result of an interaction between these elements. So to make a very simple example, let's suppose that you are seeing a face. You are seeing my face right now. My face is not just a collection of two eyes, one nose, and one mouth. The point is that we recognize that a face is a face because we see that two eyes are at a given distance that we expect. In the middle, we have a nose, and then below, we have a mouth. That is, it's not just the collection of the four elements, but it's more how they are related between them, especially to form a face. This is Also, what is more or less known, although it's not completely true, as a famous sentence of Aristotle that said that that the whole is more or is other than the sum of the parts. So the idea is like, okay, we have a system with a lot of elements. The system is not just the fact that we have a lot of elements together, but it's also the fact that these elements are interacting together in a way. And we want to study how these interactions are. And this is where network theory comes out. So, why do we study network theories nowadays? Well, let me show you a very simple example of a social network. And let's try to understand if we could, let's say, derive the information that we can derive using network without using or without considering the structure that we have below. So let's suppose that we have this very simple social network. Suppose that each one of these circle, that is, each one of these nodes are people, and that we have monitored their interaction, and therefore we know that some people are connected between them, so they talk between them, they share information or whatever, and these are represented by these links between them. So, to which person should I show an advertisement for a new product? Because, for instance, let's suppose that I have a new product. I know that these people are connected like this in this social network, and I have just money to show this advertisement to one person. Which one should I choose? Well, the standard strategy may be to go to this person here on the left. Why is that? Because let's suppose that I don't know the structure of the network. I just know that, this person has contact with a lot of other people. So 2, 4, 6, 7. So this person is connected to 7 other people. And therefore, if I show the advertisement to this person, probably this person will talk with his friends, and this will propagate a little bit in the network. Probably my ad will influence, let's say, 1 plus 7 people, which is a good number, and probably is what I care. For sure, I won't show my ad to this person here that is almost completely isolated. That person has just one friend, and therefore is doesn't seem a very good idea to show my advertisement to that person because it will talk with almost no one. So what's the point? Now, what happens if we take into account also the network structure, the whole network structure, not just the number of friends that each one of these person has? Now, this can be quite different because let's suppose that we target this person in the middle. So this person in the middle uh, has a great disadvantage, and it is the fact that he has just two friends. But the advantage is that these two friends are also quite well connected. So if you look at the whole structure, you can see that there are like two different communities, one on the left and one on the right. And this guy in the middle is the key to connect these two communities. So if I show my advertisement to this person in the middle, even though he just has two friends, these two friends on in turns, they can spread the information quite well on the left and on the right. So the point here is that probably this person here is not a bad option to spread the information, even though it just has two friends. But you cannot derive this information unless you take into account the whole structure of the network. And this is the important part of network analysis, that you cannot infer global roles or global information by just looking at the local behavior of individual nodes. So if you want to understand the behavior of the whole system, like the dynamics of information spreading here in this simple network, you cannot just look at the local information, like how many friends you have. You have to look at the global thing. You have to look at how this propagates, or how this the whole structure essentially of the network. So this is not just a matter of social networks, and you can see this in many, many different fields. Like for instance, the same could apply to a network created by the streets of a city, in which each node is a street, or even better, is a crossroad. So it's is where different streets intersect. Sorry, and then I want to see how people can move from one intersection to another one. And if I want to, for instance, decide where to put more resources or where to put police to control the movement of people, once again, I can put them here, but it's even better to put police here because then I will block the city in two parts. And therefore, if I want to check the movement of suspicious people or whatever, this will be like a bottleneck. Everyone has to go through here to go from the left part of the city to the right one. So it would be perfect to put a control here because I will just catch like everyone that goes from one side to another. Uh, you can also, of course, apply this to biological networks, like for instance, gene networks. There are a lot of works that have been done to understand how central one given gene is in one cell, and central in the sense of being able to move information or to, let's say, share information between different functions of a cell. So you may have some genes that are specific for energy production, you may have some genes that are specific for, I don't know, reproduction, but then you have some genes or some proteins in the middle that are perfect because they connect both groups of genes and they are essential in the cell, because if those proteins or those genes they are knocked down or they have any other problem, then the information cannot move from one function of the cell to another, and then you have essentially a lethal problem. Uh, you can go to, again, social network of different types, not just rumor spreading, but for instance, propagation of diseases. And as you can imagine, in the last month, this has been like a very hot topic. And the point is that, okay, if I have money just to, I have a vaccine, let's suppose that you have a vaccine for COVID-19, but you don't have money to give these vaccines to all the population. So you have to select which people are best to immunize in order to block the spreading of the disease. And once again, probably this person in the middle is a very good target, because if you can immunize this person in the middle, then the disease cannot move from the left to the right. So you are like splitting the whole network in two, and then you will strongly reduce the spreading of the disease. Um, and the second important point here is that, so the first point was you cannot infer global information from the local dynamics. You have to see the whole picture. And the second point is that relevant information, like in this case for propagation or for blocking or centrality of nodes and so forth, can be extracted from the structure of the network, as you have seen here, and you don't necessarily need to know the nature of these elements. So what we have said, what I have been saying until now, like that this element is important because it connects to different communities and so forth, is something that you can infer from the structure, from the fact that you have communities, but you don't need to know if this element is a person, is a gene, or is a traffic light, or an intersection between roads, or whatever. So the interesting part of complex network is that you can, in theory or in principle, apply them to whatever you want, uh, and you can usually disregard, or let's say in a first approximation, you can disregard what nodes and the links are. You just look at the structure and you try to infer some information from that without entering into details and about what is the dynamics of each element. If this is a person, then a person will act in a different way and so forth. So it's just, let's say, an abstract and simplified view of a system which is composed of elements, and you want to understand how they interact between them. So let me show you some more example about networks and what people have been doing in the literature. Just to be clear, I mean, complex networks as such are around since year 2000. Let's say 2006 is when this theory really started. So it's fairly recent. It's just 15 years old, something like that. So here you have examples like, for instance, you can create a network in which each node is an airport, in this case in Europe, in the US, and more or less around the world. And then you connect pairs of airports when you have a direct flight connecting them. And with this, you can more or less understand, or you can try to understand how is the connectivity, the global connectivity of passengers using the air transport. And you can detect which airports are more important from a point of view of connectivity, or you can try to understand what would happen if there is a terrorist attack or simply bad weather, important bad weather in one airport, how the network will uh, break down, and if you can still move between one part of the globe to another one, things like that. This is a another example, a very simple example with maritime trade. So instead of connecting airports, here we connect ports, and we connect them if there is, depending on the number of ships. I think this was like commercial maritime trade between pairs of airports, sorry, of ports. And here you can see that there are like some very important like maritime lanes. I think they're called like that, in which you have a lot of of ships following these same lanes to go, for instance, from Asia to Europe or to the US. Here on the top, following the coast of the US. Another example, this is, let's say, less, more fun if you want. This is a network in which each node is a music group, and two of them are connected if one of them made a cover of a song of another group. So, like for instance, you can find here the Might Be Giant, that is a group which has a lot of covers of other groups. So, as you can see, it has quite a few connections, and then you can try and understand if different music groups they cluster together. So they have like groups of group of groups that like to work together, and because they do similar styles and therefore they share songs together, or there are, like for instance, there are some people that are completely isolated, they don't like to mix with other groups and so forth. You can create networks. This is a little bit more complicated, but we will see how to do it in the third day. You can create networks in which each node is a company, and then you connect them depending on the degree of relations that they have between them. Like for instance, in this case, is if I'm not wrong, this was a work that was related with the co-ownership. So the idea is that I have a company, and then I have a second company, and this second company, even though it's theoretically an independent company, parts of the share of this second company are owned by the first one. And this creates a network that is quite complex, as you can see, and also is quite important because this could this is, I mean, this is important from the point of view of the resilience of the system, because if you have a company that owns a lot of other companies, if this first company has a problem, economical problem, like there is, a financial crisis or whatever, like the one that happened 12 years ago, then all the companies that are related with this initial company would also have problems. And this will create like a snowball effect that can propagate in the market, as actually happened 12 years ago. And the idea is then to use networks to try to understand this relationship and see if there are structures, and try to understand a priori what is the resilience of the system. You can go ahead, and this is another study that was done in 2001, and the idea was to try to understand the relationships between the people that were known to be terrorists associated with the 11 of September attack in the US. terrorist attack in the US. So the idea here is that you have all the people that were involved in the terrorist attack. The color here represents if in which flight they were inside. And then connections between them, these links are, if I'm not wrong, emails and other forms of communication that they had between them. And so the idea is that using this kind of map or of network, you can try to understand, okay, if I have a very little time to act, which person should I try to stop? So let's suppose that I don't have time to stop all of them. I just discovered that there is a plant like 1 hour before or 1 day before. Which one of them should I attack? And of course, you will try to get the most central one. Like for instance, this one seems quite important. This other person here seems quite important. You can try to understand which are the best people to, that you have to block in order to block the whole plot. Now, this network is really nice, but it has just a very important problem, and is that you can usually create this kind of network after the terrorist attack, not before. I mean, it's very weird that you have information about, if you have information like this about all the people involved in something, you can probably stop them. You don't need a nice network representation to know which one are important because you have already information about them. This network was created, of course, after the facts, so it's like, yeah, it's a posteriori analysis, which is nice, but is not very useful because things have already happened. And this is one last example that I have. This is also a real network, and this created quite some let's say noise in the complex network community because this was a network that was created with the sexual relationship in a high school in I think it was Sweden or some Nordic country. So what they did, the author of this paper, is that they went to a high school and they started interviewed all the people there, and they tried to create this map. I mean, they created this map in which you have, of course, each node is a different person, and two of them are connected if they had some kind of sexual intercourse in the past. Now, this is quite important because, as you can imagine, this kind of network is what you need to understand how to stop the propagation of, for instance, sexually transmitted disease. The point is that you don't necessarily have to tackle people with a lot of partners, but in some cases, just for instance, if you tackle this person here, this blue person here, and this pink person here, you will just break the network in 2 or 3 parts, and therefore you are sure that at least the disease will not propagate to the whole network, but it will just stay more or less contained in different in subclusters, let's say in groups of clusters. So it was quite weird because I don't know the privacy of information and all of that. Okay, the network is anonymized, but I think that the high school is known, the name of the high school is known. So it was a little bit weird at the time. This was like more than 10 years ago. But from the point of view of understanding the role of networks, and especially in this specific problem of disease propagation, was an important work. I mean, this is a very good example of why we need networks to study this. So, and just to conclude this part, we usually think that networks are something really recent, and this is actually true in the sense that modern network theory is something that was developed like 15 years ago or something like that, maximum 20 years ago. But the point is that the idea of networks, so the idea of I have a set of elements, they are connected together, and I want to study these connections because I'm really interested in the connection and not in all that's behind. It's a very, I believe it's a very old concept, and that was around since a lot of years ago, like since ancient times, even though the name was not networks or complex networks or whatever, or there was no mathematical theory, let's say, behind this. So if we go back, like a friend of mine found this, a friend of mine to be exact, found this map in the Bibliothèque Nationale de France, which is, as you can see, quite old. And the idea here is that each one of these circle, I'm not going to call them nodes because there was not a network at the time, but each one of these circle was representing a city, and then these cities were connected by lines, not links, because it was not network theory, but each city was connected with a line if there was a trade route between them. And then you have that each city is colored by a different color. And we suppose, it is believed that this was related with the kind of goods that you can trade in each city. Uh, so as you can see, this is not a network in the modern meaning of the term, but it's quite a network in the sense that it's a simplified representation of a structure in which we are not interested in the individual elements because this is not a physical representation. The distances are not like the real geographical distances between cities, but we are more interested in how all these cities are connected together and how I can move between these cities and how I can get advantage of this structure, like for instance, for um, uh, for trading and things like that. So I think it's a good example, or it's a nice example of the fact that, okay, what we are going to see in these three sessions is, of course, something modern, but the idea was there and probably is something intrinsic to the human being, it's something that makes sense to study the structure of these things. So I don't know if you have questions about that. I cannot see you, so once again, if you have question or whatever, just please let me know. Everything is clear. Okay, this was a very mild introduction, so I'm glad that everything was clear. So more or less, for you to have an idea of what we are going to see in the next days. So first of all, today we will see what is called classes of networks and a very short historical introduction and evolution. This is needed just because it will give you a better idea of different types of networks and why networks are not as easy as it may seem, or why we need some simplifications or some null models and so forth. Because let's say this we will need in the second and the third day. In the second day, so next week, we will see some basic topological metrics, and topological metrics are just metrics that we can calculate, numbers, if you want, that we can calculate on networks, and they will tell us something about their structure. And the third day, we will especially see some applications, biological application. We will see some example on how to reconstruct a network and, of course, how to analyze them. But let's start with the classes on network and how this started. So, beside what I told you of Euler that started with the idea of graphs, okay, so we have graphs and so forth. This was just, let's say, the first idea, the first time that the term graph was coined or was used in some context. Then a lot of time had to pass, more or less 2 centuries before people started to analyze networks again. Well, graphs in this case, because this was still in mathematics. So people started to analyze graphs again and started to do something with that. And this started with these two guys that you have here on the screen, Paul Erdos and Alfredo Reni, that decided to, well, or started analyzing random graphs. So first of all, as this is a topic that will come back several times in this talk, I don't know exactly why, but for you to know, Paul Erdos, he was an incredible genius. I mean, one of the most important mathematicians of all time. Probably, I would say after Euler was like the second most important of all time. But it was completely crazy. And this is something that I don't know why, but a lot of people working in networks are quite crazy. I'm also working in network. I don't know, maybe I'm crazy too. But here you have some things that, some sentences that were attributed to him, like a mathematician is a machine for turning coffee into theorems. He took amphetamines, was perfectly fine with that. Children were referred to as epsilons. He was a mathematician, it's clear. Women were bosses who captured men and enslaved them by marriage, things like that. So it was quite crazy. Um, in any case, what they did was, Erdos alongside with the Reni, they created the concept of random graph. So a random graph is something very simple. Let's suppose that we have a set of nodes that represent whatever we want. They can be people in a social network or genes or proteins or whatever you want. And we just start adding links at random with some fixed probability. Let's call this probability P. So I don't have a structure. Actually, this is the opposite of a network that we want to analyze. So let's suppose that we have a social network or a network of genes. We extract this network and we want to analyze the structure of this network. Well, random graphs are exactly the opposite. They have no structure at all because by definition, all the links are just introduced completely at random. Uh, so why are these useful? We will see why, especially tomorrow, sorry, in the next section. But they have some advantages, and one of them is that metrics can be approximated quite well. So let's suppose that I want to see what is the average distance between nodes. And by distance, I'm introducing something that we will use next week, but just for a very simple idea, by distance, I mean the number of jumps or of links that I have to take or to do in order to move from one node to another. So let's suppose that I am in this node here, and I want to go like here, for instance. Okay, so I have to take one, two, and three jumps to go there, or yeah, jumps, hops, or however you want to call them. So the distance between these two nodes will be three. If I want to move from this one to this one, the distance will be one because I have a direct connection. So imagine that you can see this as the, I don't know, the number of flights that you have to take to go from one city to another. So for instance, if you want to move from Madrid to Berlin or to London, it will be just a distance of one because you just have to take one flight. You have a direct flight. And if you want to go to a smaller city, then maybe you don't have a direct flight and you have to take two or three or the number, whatever is the number of flights that you need to take. So the distance, this number of flights or number of jumps, or more technically, the distance between pairs of nodes is proportional to the logarithm of the number of nodes. Now, this is quite important because what it's telling us is that if you increase the size of the network, you will need more time or more jumps to go from one part of the network to another one, but not as long, but not as much as the number of nodes. So if I increase the number of nodes by 10 times, so let's suppose I have 10 nodes, I will need an average of two jumps to go from one to another. If I then multiply the size of the network by 10, so I go to 100 nodes, I don't need 20 jumps on average to go from one node to the other because there is this logarithm. It's not linear, it's sublinear. So maybe I will need three or four. So this is quite important. The distance between nodes in a random network, and we will see exactly why, is not proportional to the number of nodes, but is sublinearly proportional to the number of nodes. So even if you have a huge network, the distance doesn't grow as fast as the number of nodes. Do you understand more or less this concept? Is okay, it's not difficult, but just in case, just to be sure. On the other hand, you have another metric that is quite important, and we will see it next week, is the clustering coefficient, that is more or less the number of triangles that you have in the network. Now, in random graphs, you almost don't have triangles. Why? Because in order to have a triangles, let's suppose that I want a triangles between these three nodes. I need a link here, then I need a link here, and I need a link here. That is, the probability of having any triangles is proportional to the cube of P, where P was the probability of just having one link. And therefore, as you can imagine, this probability is very small, especially because P usually is a small number. So the probability of having a triangle is almost nothing. Well, it's very low. It's not nothing, but it's very low. Okay, great. We have these random graphs that they are useful at some point. We will see next week that they have some usefulness in them. But okay, so this was the first approach. And we are talking about, this was like 100 years ago or something like that. Well, probably a little bit less. So this was just a first approximation about graphs. Let's start with graphs that are completely random. And they got these results. In parallel, there was another possibility that were regular graphs. So let's suppose that I have a bunch of nodes, like the ones that you have here in the screen, and then I create a rule to connect them that is, in some sense, just the opposite of what we had before. So before was just, I will introduce links at random. Now is more, I will introduce links according to a rule. And the rule is that I will connect each node with its neighbors. So like, for instance, this node is connected to its neighbor on the left and its neighbor to the right, and so on and so forth until the whole network, until I create this kind of loop of circle. I can also do this to second neighbors. That is, this node is connected to this one and to this one. So it's like, the second neighbors. It's like if these are a bunch of people around forming a cycle, well, they are connected to the first neighbor. They can just talk with the people that they have just, let's say, at their side, but they can also talk with the people that are slightly far away. Now let's go back to the metrics that we have defined before. So the distance between nodes, in this case, uh, as you can see, is linear with the size of the network. Why? Because if I have to move from the left to the right, I have to go through almost all the nodes. Well, I can actually jump over, take the second neighbors, so I just need 1, 2, 3 links. But if I make this network the double, so I double the size of the network, I will also have to double the number of links that I have to take in order to go through all the upper part of the network. So in this case, the average distance between nodes grows linearly with the number of nodes that I have in the network. So from a point of view of propagating information, this is not really good, actually. So regular graphs are not really efficient. On the other hand, how many triangles do I have in this network? Well, actually, I have a lot of triangles because they are there by construction. So like, for instance, this node is connected to the two neighbors, and then these two neighbors are connected between them. So this form a triangle. So as you can see here, I have a lot of triangles. Uh, I gained somehow triangles, but I lost in efficiency in connecting, in connecting nodes between them, in moving between nodes. Okay, we have these two possibilities, random graphs and regular graphs. Just to sum up, in random graphs, you have that the distance between nodes, the average distance is small, and the number of triangles is also small. In regular graph, you have that the distance between nodes is higher, grows faster, let's say, but also the number of triangles is higher. Okay, so what happens with real networks? That is, let's go out in the world, let's try to take some social networks or some other networks, transportation networks, and so forth. Let's try to see if they fit in one of these two groups. And so for that, we have to go to an experiment that was done in the 60s by one quite famous psychologist, if I'm not wrong. I don't know if it was psychologist or sociologist, but in any case, his name was, I think, I don't know if he's still alive, Milgram. And Milgram was also completely crazy. I don't know why, but people working in networks, they are crazy. And he's famous for a couple of experiments. The first one that has nothing to do with networks, but probably you know it, is the famous Milgram experiment, in which essentially what it did was it took a set of participants, and these participants were asked to participate, to be, let's say, the active part in an experiment. And the passive part was a guy who was an actor that had to do some very simple task. He had to learn something. And the participant, the real participant, so the person that was invited to do the test, had to check whether the actor was doing the task correctly or not. And if the actor did it the wrong way, the participant had to administer an electric shock, like, like a small pain, just to no, you are doing it wrong. So he had to like give this mild electric shock to the actor. Of course, this was not true in the sense that the actor was really an actor, so he made mistakes on purpose, and he faked like the reaction, like the pain when the electric shock was applied. So actually, no one was harmed in this experiment. But the point is that the participants were told that if the actor was still doing mistakes, they had to increase the voltage and the intensity of the electric shock up to a point in which it was clearly labeled as potentially, potentially, let's say, fatal. So they could result in the death of the other person. And the whole point of this experiment was to check which percentage of people would follow the order, even though they knew that what they were done could result in the death or at least in important injuries of another person. And as you can see here, like more than 60% of the people reached the severe and deadly, let's say, electrical shock. So this explained like why you had things like Nazism or things like that, because people tend to follow orders if they are given by some, they say that some people by some people that they consider like important, even though they know that this could have very bad consequences. It's a very weird experiment, and from a sociological and psychological point of view, it was super important. But still, the experiment was like subministering people with electric shocks, so it was quite weird. In any case, Milgram was mostly famous for this experiment, but the important one for networks is the second one, the Milgram second experiment, in which essentially he took a set of letters, and mailed them to other people in the US at random. Now, taking into account that this was in the probably 70 or 80, I'm not sure of the year. So it was real mail, not email, so real physical mail, let's say the old style one. So the point is that he prepared this set of letters. He sent these letters to a bunch of random people in the US, in one coast of the US, I think it was the West Coast. And inside each letter, there was a text asking the people, the recipient of the letter, to forward the letter to one person that was living in the opposite side of the US, was a lawyer, I think, in the East Coast. And the point was that you cannot just, if you receive this letter, you cannot just look for the address in wherever you could look for that and send directly the letter to that person, to that lawyer, but you could just forward the letter to another person that you knew and that you consider was closer to that person. So let's suppose that you received the letter. You are in the east coast of the United. Sorry, you are in the west coast of the United States. You don't know this lawyer, but maybe you have a friend who is a lawyer and lives in New York. So probably the reasoning could be, okay, if I send this friend of mine, he's a lawyer, he's living in the same city of this lawyer, so probably they know each other. And then you can send the letter to this intermediate person. And the idea is to count how many jumps you need to cross the United States. So if you wanted, this is a first example of a social network because you are connecting people that know each other, but and you want to see how much links you needed to go from one side of the United States to the other. Now, what was impressive, now it's a very well-known phenomenon, but at the time was quite shocking, is that the number of intermediaries that you need to connect the two extremes of the United States was six, well, at least the median. So it means that if you start with any people in the United States, and in 6 steps or using 6 friends, you can reach any other person in the United States, which is quite counterintuitive because there are a lot of people in the United States, but you don't need so many in order to create this kind of chain. This is, of course, this was a very old result obtained with regular mail, so it was not really, let's say, reliable and so forth. But this has been studied with the real data. Like, for instance, if you go to social media, of course, you can take Facebook and you can calculate what is this hop distance, that is the number of steps that you need to go from one person to another one. And as you can see, with time, Facebook got more connected and the more or less converged to 5. So with 5 steps, you can reach any person in Facebook, more or less. And then also it was done with other replica of the original experiments. And also you can see that even for the United States, you are around 4, 5, between 4 and 5 steps to reach any pair of people. Then, of course, there were a lot of games done around this. Like, for instance, you have the social network of Kevin Bacon, the actor, and the idea is, okay, you connect actors that have, you connect two actors when they participate in the same movie. And then you can see that Kevin Bacon, if I'm not wrong, was the actor most well connected in Hollywood. That is, you just needed to jump across a couple of actors to go from anyone to him, like inside the Hollywood, let's say, network. And just to test this theory, now I ask you, okay, let's see a real network, a real social network. What do you think is your distance with Obama? That is, how many jumps, how many social jumps you have to take to go from you to Obama? But give me a number. What is your estimation? It's quite. Sorry, say again. Yeah, it's difficult, but I don't know. Give me a number. 15. 1 5. Okay. No, I'm sorry to say. I mean, I am happy to tell you that you are quite pessimist because actually your number is way lower. I also thought that my distance with Obama was huge, but actually, no. What I discovered a few years ago is that I know this person, Carlos Alvarez, who knows one lady who was in the staff of I think in the re-election campaign of Obama. So technically, I am distance 1, 2, 3 from Obama, which means that as you know me, you are a distance 4 from Obama. So you are very close to Obama. So of course this is quite important. It doesn't mean that I can take my phone and call Obama. I mean, that can try. Probably will never take my phone. Uh, the only thing that it means is that I can try. If I want to reach him, I can send a message to my friend, hoping that he will forward this message to this lady, and this lady will then forward the message to Obama. Of course, the probability of this happening is essentially zero. I don't think I can reach Obama that easily, but it's quite surprising to see that in real network, the distance between pairs of people, even between me, that I am no one, and Obama, no former president of the US, is not as large as you can expect. It's not 15 or so steps. It's actually 3 or 4. And of course, this is related to the fact that nowadays we are in society that are very strongly connected. We all know people from different countries, and therefore the distances are really are. Let's say the social distances are not really related with the geographical distances. You don't. I know people from China, so I mean, I know people living in China, so distances are in the virtual world are completely different. And okay, so this was about physical, say that is distances between in a network. But what about triangles in a social network? Well, this is very well known since a lot of years ago, and this is what is called triadic closure. Or in more simple terms, the friend of my friends are also my friends. So let's suppose that I know people in UPM. I know Alejandro, I'm his friend. I'm also friend of Ernestina, who is another professor at UPM. Well, it's quite probable that they know that they will know each other. And actually, it's the case because we were all in the same research group. So the point is that if we go to a social network, what we have is that the average distance between nodes is very small, is smaller than what we may expect, and the number of triangles is actually higher than what we may expect. Um, and then we have a problem, as you can see, because we have two models. We have the random graphs and the regular graphs. And as you can see, they have nothing to do with the real networks. That is, real networks have the low distance that you can see in a random graph, but have the high number of triangles that you can see in regular graphs. So real networks are like a mix of both of them, or they are none. So, but the important point is that um, 15 or so years ago, people started realizing that, okay, we have some graph types, regular and random one. But then if we go and see, when we look at the reality, this reality has little to do with the models that we had. So as a minimum, what we need is a better model or something like that. And so at this point was when in 20 years ago, actually, this first model, this quite important model, was proposed by Watson-Strogat, and this is called the small world or the Watson-Strogat model or the small world model. And essentially, the idea is that I started with with a regular graph, like the one that I have here. So each node is connected to the neighbors and to the second neighbors, for instance, something very simple. And then what I do is that with some probability, I take one link, like the one that was here, I delete it, and then I create a random link in the middle. So this is actually a mixture between the regular graph that is here on the left, and if I do this rewiring process a lot of time, I will end up with just a completely random network. So I'm moving between a regular graph and a completely random graph. And the nice point is that, without entering into too many details, but there is a transition in the middle. You have a point in which, if you rewire a given number of links, you keep the triangles that you have in the regular graph, but you create shortcuts between nodes. So moving in the network will be way easier. So the result of this is that you can have a lot of triangles, like here, for instance, you have a lot of triangles, but also you have a smaller or a small distance between nodes. So you are recovering more or less the what you observe in real network. And this is what is called the small world phenomena or property of a network. When you have a high number of triangles and at the same time a small average distance between nodes, the two properties together. But there is still a problem. So if I take a random network or a network created with a Watson-Strogat model, I will have a distribution of the number of neighbors for each node that is more or less this. What I mean by this is that let's suppose that I take one node. I counted the number of neighbors that it has. This is called the degree of the node. The degree of the node is just like the number of friends of that specific node. Then what I can do is that I can plot a probability distribution. And if nodes are connected at random, so in a random network, what you will find is a distribution like this one. Is a technically is a Poissonian distribution, a Poisson distribution. If you are interested, you can check why, but it's not really important. The important point is that um, you have that a large number of nodes with a given number of friends and very few nodes with a high number of friends or a very low number of friends. So if I just put links at random, uh, the, let's see a very simple example. Let's suppose that I have 100 nodes and I put in the network 1,000 links. Most of the nodes will have 10 connections just because there are 10 for each one of them. So if I put them at random, I expect most of them of having 10 connections. Just by chance, some of them may have 9 or 11, a few of them 12 or 8, but it would be extremely strange to have one node with 900 connections because it's really unlikely that all the connections at random will end up in a single node. Are you following me? No, it's like, I mean, more or less there will be distributed among the nodes of the system. So I will have a distribution that is like this. So will be centered around a value, and this value will be the number of an average number of connections. But if I go to the real networks, what people started finding is that this is actually not true. That is, let's suppose that you go to social networks like Twitter or Facebook or things like that. You will find that there are some people that have a huge number of friends. Like, I don't know if you go and check, well, friends or follower or whatever. If you go and you check, I don't know, I think that is Lady Gaga that has one of the highest number of followers that is, I don't know, million or probably, I don't know, hundreds of million of people following her. And on the other hand, most of the people have like just a bunch of connections. Maybe they have 10 followers, maybe they have 5, or maybe they don't even have them followers at all. I guess that most of the accounts are just there. They follow people, but they are not followers. So you don't have this distribution because this distribution it will be like everyone in the world has 5 friends. No, no, it's not actually like that. There are a lot of people that have a lot of power, that have a lot of connection, and most of the people have almost no connection. So the degree distribution, as it's called, is something more like this. So you have a lot of people with 1 or 2 or 3 connections, and then a very few people, a very few like set of people with a lot of connections. And this is called a scale-free distribution because in this case, well, without entering into details, but the point is that there is no characteristic scale. you cannot say like, oh, on average, people have 5 friends. No, because there are some people that have hundreds of thousands of friends, and most of the people have zero. So it doesn't make any sense to say five, because five is not representative. There is no characteristic scale of the system. Now, this is something that actually has been shown in very different systems, like in protein-protein interaction networks that we will see in the next days. If you go to the power grid, it's the same. And these are networks created from notes in songs of sonatas from Mozart. So in very, very different fields, you have this kind of distribution of the structure. And this corresponds to a real structure that is more or less like this. That is, you have one node in the center that is usually called the hub, that is connected with a lot of other nodes. And then you have a lot of nodes that are like just in the periphery, that are just connected with one or two other nodes, and probably will be connected with the hub. So if you think about that, think of any country air transport system, like in Spain, you have that the airport of Madrid Barajas is very well connected with all the cities in Spain, but a small airport like, I don't know, Vigo, yeah, Vigo will be connected with Madrid, but they won't have a lot of other flights. So you have this like centered star-like structure. And in social networks and in many other networks, actually, it's more or less the same. You have this kind of structure. Uh, in order to explain how this kind of networks can appear or have appeared in reality. Two researchers, Barbasi and Albert, develop a model that is very famous and is called the Barbasi-Albert model. Of course, people working in network, they don't have a lot of fantasy when it comes to assign the names. You have the Watson-Strogat model, and this is the Barbasi-Albert model. And and the model is very simple, but allows you to recover this fact that some nodes are more important than others. And the idea is that we start from a seed, and the seed is just we start from an initial small network. We add a node, and then we decide to which of the existing nodes that we add in the seed we want this new node to be connected. And we connected this new node to the old one in a way that is proportional, with a probability that is proportional to the degree, that is to the number of connections of those nodes. So in this case, it's very simple. This node here has two friends, two neighbors, let's say, and these two nodes here have just one neighbor. So this node being more central is like has like the double of probability of being of receive the connection than the other two. So this node will probably connect to this central one. And why is that? Think again on I don't know, on air transport network. If I am a new airline and I want to create a new connection, let's suppose that I start working in a small city in Spain, like I don't know, Vigo, the previous example. I'm a city that is not yet connected with any other airport, but I want to create a new connection. Well, probably I will want to connect with a central city or a central airport. I don't want to connect with another city that is very small. They have no connection to other cities. They have they have very few passengers. I want to get connected with Madrid or Barcelona or I don't know, London or something like that, with big cities and big airports. So my first attempt will be to try to connect with the big nodes of the network, the nodes that already have a lot of connections. And this is what this algorithm does. So I try to connect this new node to those nodes that are more connected, or at least with that probability. So I will connect this one, then I will get a new node, I will try to connect, and so forth. And this is synthesized in a very simple phrase, a very simple sentence that is that the rich gets richer. Because if you are a node in the network with a lot of connections, more people will be willing to connect with you. And therefore, if you are rich in the network, you get more and more connection and you will get every time richer. Um, and so this is the fact. So we moved, let's say, historically from very simple models, or even if you want, when we had no models at all. So at the beginning there was Euler that just defined, let's create this kind of structure that are called networks or graphs at that point. Then mathematicians started creating very simple models that were actually not useful to model real world systems just because they were too simple, like random graphs and regular graphs. But it was a start, and they started also defining some metrics, some topological metrics to describe this graph. Then we moved to complex networks, and this is where statistical physicists entered the game and said, okay, now let's try to create models that are able to mimic the structure of real systems. And then you have the Watson-Strogatz model in which you can recover the distance, the average distance between nodes and the triangles. And finally, you have the Barabasi-Albert that is able to recover this slope in the degree. That is the fact that there are some nodes that are really important and some other nodes that are not that important. And with this, you can more or less model a lot of different networks, from social network, technological network, biological network, more or less. Like, for instance, friendships, they have a lot of, there are some hypotheses that you cannot fulfill with this kind of model, but more or less you can recover the main characteristics and you can start the analysis from that. So this is all actually, I think, for the questions about this part. Okay, so you see that, I mean, networks are, I would say, that are an easy topic, but you will also see in the next days that they can be quite powerful. So is the mathematics that's behind networks is easy, but they allow you to really extract some fundamental aspects of the interaction that you have in a system. And this can be really useful with some system in which interaction are very important. Like if you think on biological systems, for sure you will realize that, yeah, you have elements, but the interaction are probably even more important than the elements themselves. So if you agree, I will say let's take a 5 minute break, also to recover my voice a little bit, and then we move to the program so you can see how to easily represent a network and start playing with them. Okay, so see you back in 5 minutes, more or less, 25, let's say. Okay, perfect. Okay, I'm back. You are also back? Okay, perfect. So, okay, let's see this program, Cytoscape. As you will see, Cytoscape it has a couple of advantages. First of all, it's very easy to use. More or less, it has a couple of tricks and things that are not super clear, but usually it's very easy to use. Was developed with biological networks in mind. So it has a lot of function, like for instance, to connect to databases in the internet, download the data, represent them. So it may be especially useful if you plan to analyze biological data. That's why also it's a good thing. And if you have some how to say style, or if you know how to do good representation, you can get very nice images of also of networks, which is not my case. I'm usually very bad at representing things, but I mean, I will show you the tools, and then each one of you will will do what you can, let's say. So, did you install the program? Can you run it? So, have you run it? Okay. So you see my screen more or less, right? So you see my what I have now in the screen. Okay, so first thing, of course, we have to load the network. So in this case is cytoscape file, uh, import network from file. Because we want to import a network that is a network that we have defined in a file like this one that I sent you, network.txt. Um, Otherwise, you can also open networks from the internet and so forth, but let's keep it simple. So as you can see, the structure of the file that I sent to you is very simple. It's just the name of the first gene, that is, of course, fake. I mean, it's not a real gene. Then the name of the second gene, and this defines which one are connected. And then a number that defines, let's suppose, how strongly connected they are. And we will see this in the few, like in the following classes, how you can define this number. But right now, what we are just interested in is the fact that you have pairs of genes that are connected together by a number that gives us the strength of this interaction. So if I open it, you will see that this dialog will open. And here there is, first of all, something important to do. If you go to advanced options, you have to deselect this use first line as column names. Because right now, if you see, so if I select this one, it will tell me that the name of the first column is gene 1 and the name of the second column is gene 4. That of course is wrong because we don't have column names. So just deselect this. So everything that is inside the file is just data. There are no column names. And here you can see that is the first column, the second column, and the third column. So data are more or less organized. Then, if you was right click on column 1, of course you can change the name of the column if you want, but what is most important is that you have to select, it's already selected, but just in case, this green circle, that is the source node. So we're telling him that, we're telling the program that the first column is the gene from where the connection starts. So I select this just to be sure, okay? And then in the second column, I have to do the same, but in this case, I have to select this red target that is called the target node. So essentially here what I'm saying is, okay, look, I want each line is a connection, and the connection will go from the gene in the first column to the gene in the second column. So in this case, from gene 1 to gene 4, from gene 1 to gene 5, and so forth. The third column is just an edge attribute. Okay, it's an attribute that we will assign to each connection. That's okay, we can leave it there. Nothing more here, you can just click OK. And if everything goes well, you will have a kind of ugly network, like the one that I have on my screen. Do you have something similar? Okay, perfect. So don't worry about the fact that you cannot see anything. That's okay. Just to simplify things at the beginning, if you go here in Cytoscape layout, here you have a set of algorithms that you can use to reshape or to, let's say, look. It's called layout. I mean, I don't know what else, what word I can use instead of that. So to position nodes in the space in order to make the graph a little bit better. Like for instance, you can use the grid layout, and then each node will be in a position in a grid, a very simple grid. Usually is not the best option. Circular layout, very simple, and here is more or less easier to understand. You can try just different like hierarchical layout. This takes a little bit longer to calculate. Yeah, actually quite longer. That's weird also because I have the CPU is working at like 100%. Okay. Yeah, the problem is that I'm also recording the video, so it's like working. Yeah, like 60% of the CPU is just because of that. So okay, I will go back actually to the because this layout is it's ugly. Let's go to the I don't know circular one or whatever. Actually, usually one that is quite good is if you go to edge-weighted force layout, whatever spring embed, something like this. Meh, more or less, more or less. So just if you do this, you can see that in the center there is a set of nodes of genes that are quite strongly connected together. And then in the, let's say in the outskirt of this network, we have some genes that are not very well connected. Like, I don't know, here I have the 44 that has just three connection, the 97 that has just three connection, and then here in the middle I have, it's like more dense, it's denser somehow. So before going, before going to the to change the graphical representation, I sent you as a second file. So what we can do is import table from file, and you select the second one, that is this property.txt. And here, the only thing that I have is a property, a number, let's say one single number for each one of the genes, for each one of the nodes. Uh, I don't care what this represents. Let's suppose that we are talking about genes and that this number tells me the function, such that if the value is zero, this gene is involved in the energy production of the cell. If it's one, is involved in, I don't know, reproduction. If it's two, is signaling or whatever. So we don't really care. The important fact is that I'm associating to each node one attribute. Then I open this. I have to do the same trick as before in advanced option. Deselect the use first line as column name. This is important. Okay. And then here you can see that I have column one are all my genes, and it's telling me that is the key. So it will try to match these names with the names of the nodes that we loaded at the beginning. Column two is just column two is an attribute. It's okay. I don't care for that at the moment. I load it and nothing special happens. But now what we can do is that we can go to style. If you see here on the left, we have this style like selection. One good and bad thing about Cytoscape is that they usually update the program fairly frequently. So it happened to me of opening the program one day, everything was going perfectly, and 1 week after I downloaded a new update, I opened the program and I couldn't find any option just because the interface was completely different. So just be advised that it may happen to you, but usually the functions are there. They just move where they are, things like that. So if I go to style, and here I select nodes, here you can see that there are a set of like properties or properties of the nodes that I can change. So for instance, if I don't like the shape of the node, if I click here in the felt value, I have a set of options. Like, I don't know, I want all the nodes to be triangular. And then you can see on the right that the representation will change. Uh, this is not really important, but what is important is that I can link one attribute, one property of nodes to the values that I have imported from file. So if you go, for instance, here, let's select this shape. See that on the right, I have this like a small triangle. So I can open this. And here I can select a column that is an attribute that will define the shape of the nodes. So like in this case, I select the column 2. And then, trust me on this, I would do discrete mapping. So if I select discrete mapping, here I have the 4 values that I had in the file, 0, 1, 2, and 3. You remember that each node was associated with a value that was 0, 1, 2, and 3 in the second file that we loaded. Okay, and in the discrete mapping, now I can define one shape for each value. So let's suppose that when the mapping, that is when the attribute is 0, I want, I don't know, a diamond. Then when this attribute is 1, I want an ellipse. When the value is 2, I will select a rectangle. And when the value is 3, I will select, I don't know, something, an octagon, for instance. Okay, when I do this, you can see here in the representation on the right, each node changed according to its value. So if I select gene 97, actually you can go here. Yeah, node table, gene 97, the name is gene 97 because we didn't change the name. And the value that I uploaded was 3. Okay, so its shape is an octagon. And you can see here that it's actually an octagon. So here you can easily change the size or the shape of nodes depending on what they do. But let's do something more interesting. Like for instance, we have these connections, but these connections are all the same. While we loaded a file in which each connection was associated with the strength of the connection. So if we go here to edge, also in this style thingy, in the bottom part, you have edge. Here I can select the properties of edges. Okay, what I can do is that I can say, first of all, select just edge color to arrow, even though we don't have arrow, just in case. If I select this, I have then color unselected. This is the color of all links. So I can select red, for instance, and then suddenly all my links will be red. Okay, but useful, but not that much. What I can do is that I can expand this and say, okay, now the color will depend on column 3. That was the weight that I imported. And the mapping type in this case, let's make it continuous. And let's double click in the mapping. Yes, it's double click. Okay. So essentially here, the point is that I have a continuous mapping in which the program will like morph the color depending on the value of on the strength that I have for each link. So I can say, for instance, I don't know, for very low strength, I will put a very like mild gray, something like this, so it will be almost transparent. And yeah, actually, I don't know. I like these colors more or less. I don't know. They're not that ugly. If I say okay, so essentially links that are not very strong, like very mild links, will be light gray, and then it will move to a darker color the stronger is the link. So more or less you can have a visual idea of the connection. But you can do the same with, I don't know, width. Width is the width of the link. So the how how the width of the line that represents the link. I don't know how to say this in other words. So how big is this line essentially? I can do exactly the same trick. So I would say that the width of the line depends on column 3. The mapping type is continuous. And then, okay, this is ugly. Why is this ugly? Because it goes from 10 to 30. And in the original plot, I think it was 2, the width. So let's say that I will go from 0.5. I just double click here in the rectangle, in this square. I double click here and I will say 3, for instance, or something more probably. Let's say 6. Okay, well, not too shabby. Essentially, you have that. You see that there are some links that are really thin because they are not. Wait, I'm moving this because they are not important, and then there are some links that are way more like thick because they are more important. Uh, of course, now that I made this mistake, you can actually see you that you can select one node and move it around if you don't like the standard layout, like because maybe you say, okay, I don't see the names of these genes, so I can just select and move this one because I want to have something clearer. Um, and then I deselect so the color will be okay. Uh, you follow me up to here? Okay, if you actually look in the web page, probably you have seen it in the web page of this program. They have examples of networks, and some of them are, I don't know, they're like art. I mean, they're very nice, they're super nice. I don't know how to make such a good representation. I'm not, my artistic skills are not that high, but if you know how to use the program, it's very nice. But this is more or less the basics. Let's do something more sophisticated. Like if you go here below in the bottom part, see that I've selected node table. So node table is all the properties that I have for nodes. That in this case is just the name and this number that we have uploaded, that we have loaded from the file. Not really interesting. If you go to edge table, well, you have essentially the gene one interacts, it's the interaction here interacts with, so you have gene one interacts with gene four, and then you have this strength that is the last column. Okay, let's go back to nodes. Now, what I can do is that in tools, uh, you can select analyze network. Actually, tell me if you can, if you have this option. Okay, because as you can see here, side note, there is an app manager, and the idea is that you can, they have a repository of different like programs and libraries. You can download a library and you can add the new functionalities to the program. It's actually quite nice. The only problem is that I never remember which one I downloaded and which one come from the original version. So I think that, for instance, I have this Wi-Fi layout algorithm that probably you don't have, but okay, nothing important. Hmm? You don't have that. Okay. In any case, if you go to analyze network, um, it's not directed, so just say okay, and it will do some things. Actually, here on the right, you have some more information, but these are examples actually of topological metrics that we will see in the next section next week. So don't worry too much about them. It's not important. Well, you can see if you want the number of nodes. That is the number of nodes that you have in the network. This is a very simple metric. Number of edges, number of links. We have a 500, things like that. Now, what is important for today at least is that here suddenly in this table you have a lot of parameters. And why is that? Because the program calculated some parameters for each node and created and populated the table that you have there with those parameters. And you have things like, I don't know, clustering coefficient that maybe sounds familiar from before. It's the number of triangles that you have around one node. But let's focus, we will see all these metrics next week, but let's focus on the degree. As I tell you, the degree is just the number of neighbors that a node has. So the number of connections is probably the simplest metric that you can have. Now, you can see that there is one node with 70 connection, 46, 42, and then it goes down. And there are a lot of values. Okay, as this is already now a property of the node, what I can do is that I can change the color of the nodes depending on the degree. So go and do that. If I go here on the left to node, I have a fill color. Okay, let's change the fill color. Now, if you select the column, as you can see, you have a lot of properties, all these properties that the program calculated. Let's select the degree. Mapping type, continuous. Once again, I want this nice uh, like progression of color. Then I double click, and here once again your artistic like predisposition will help you, not me. So in this case, I will select once again gray, and I will select here red probably to make like clear. Yeah, it's absolutely ugly, but whatever. So the important point, what I want to show you is that here on the left, we have low degree nodes, and here on the right, we have high degree nodes. So I will just plot in gray or some not important color, the nodes that are not really connected, and then I will put here in red the ones that are really important. And actually, what I will try to do, I will try to add another why add okay, let me do like an orange. So I want just to, okay, do something like this. Okay, so suddenly you see that we can see the difference between nodes. You have nodes that are like very peripheric nodes. They're connected, but they're not that important. But then we have this gene 6 that is really in the center, and this is really highly connected. And then we have also 4, 7, 5, and 12 that they are not as strongly connected as no as gene 6, but still they are important. So from this, you can already see that this network is probably a scale-free one. That is the last category that we have seen. That is, there is a few nodes, especially node 6, that has most of the connection. Well, in this case, it's not most, but is 70, so well above what you would expect. And then you have a lot of genes that just have 2, 3 connections, things like that. Now, if this was a real data set, and these were real gene data, as you will analyze in a few weeks from now, this will tell you something quite important. Like, for instance, if these are data about an healthy cell, you know that gene 6 is quite important for the cell. And this is called what is called the problem of lethality. So if you do something bad or do something in general to this gene 6, you will probably kill the cell, because this gene is like in the middle of everything, of all the processes. If you kill or if you delete or do something to this gene 44 that is here isolated, maybe it will have some effect in the cell, but it will not be lethal, probably. There are studies that study this, but you get the idea. So there are genes that are more central or more important than others. And on the other hand, let's suppose that this is the network that represents how a type of cancer interacts with the cell. Then in this case, you want to attack gene 6, because gene 6 is probably the gene that is allowing the tumor to grow in the cell and to interact and take advantage of the cell, of the health cell. So what you want to do is actually to attack gene 6, because you want to kill the tumoral cell. This is a very simple example. Just by plotting a network, we move from the file that I sent to you, the TXT, that is almost impossible to understand. I mean, it's just, a bunch of lines and numbers that is not really nice. to something that is graphical and that with some better representation. I mean, you see that there is a structure and you can start inferring some information from this. And then, of course, the more time you spend in filtering, in changing the colors, in doing things, you can do some really nice stuff. There are plenty of options here that uh, if you are like if you have time, you can try and different layouts and so forth. So I think it's a nice program, and especially as you can see, it's fairly simple. That is when you know the program, in 10 minutes you can load a network, apply a style, and you have a nice representation, and you have a first view of the network, let's say. Okay, I don't know if everything was clear. Do you have any question? Do you want to do something to this network? I hope you got better representations than me, than mine. That mine is actually, yeah, this red in the center is ugly. It's awful, but whatever. Okay, so I don't know if you don't have more questions about this. In any case, if you have any question about the program, let's suppose that you during this day you during this week you play with it, you can actually load any other data. If you are curious, you can load the data from public databases, and especially if you also have some kind of data like this from your studies or from your research, what you have done in the past, just try to load it here and see what happens. And if you have any problem, I will be monitoring the team's channels. So whatever you want, you can just send me a question. And the next week, what we will do is something like this table that you see here. So we will extract metrics from the network to see what are the most important nodes, what are the general properties and so forth. But we will do it in Python because it's better, because then you can do any kind of analysis if you want. You can do data mining or that, machine learning, whatever. You know, this program is nice, but it's limited to just this environment, let's say. Okay, so yeah, so yeah, I agree. There is no, um, yeah, there is no way of doing that. So next week and especially the week after, we will see how in Python you can create this kind of file. But if you have a data set in Excel, there is no automatic way from Excel to export in this format. Uh, yeah, yeah, I'm sorry about that. There is no, so you have to there is no option. I mean, you have to create that file. The file that Cytoscape needs is always first column, like node, tabular or comma, whatever node, and then intensity or strength, whatever. And just one thing, you can, of course, save the project here in Cytoscape. You can export the network to other format, but also what is most important, I guess, is export the network as an image. So it allows you to take this picture that you have here and save it to a uh, JPEG file or whatever you want for further representation, or if you want to include it in a presentation or whatever. But yeah, the input file must be essentially in that format, and there is nothing that we can do to avoid that. So yeah, that's unfortunate, but you need a network essentially. You need that format. Okay, any other question? Okay, in that case, you're welcome, and let's see next week, in 1 week. Perfect. See you. Have a nice week. Bye.